What if there were devices that could solve problems in the blink of an eye that would take even the fastest supercomputers billions of years to solve? What if we had computers so powerful that they could simulate all of nature's processes and provide us with all the answers to the big questions of humanity, from the creation of the universe to the evolution of life? Well, then we would have arrived in the exciting world of quantum computing. Indeed, scientists at the famous University of Oxford have now achieved a groundbreaking milestone in this field, connecting two quantum computers for the first time to solve a highly complex quantum task together. In the course of this, a quantum logic gate was teleported over a distance of 2 meters. But how does something like this actually work? Why are quantum computers suspected of radically changing our daily lives in the future? And what actually gives them their incomparable computing power? It's a report that makes you sit up and take notice. A few weeks ago, the leaders of Google Quantum AI announced that their quantum processor, Willow, solved a task in just 5 minutes that would take the world's best supercomputer, believe it or not, 10 quadrillion years. That's a 1 followed by 25 zeros. But how is it that quantum computers turn even the most powerful computers of our time into lame snails? To understand this, we first have to visualize how our current everyday devices work in the first place. Whether you're watching this on your laptop, cell phone, or tablet, all these devices work with bits, units of information that can only assume the state of 1 or 0. In today's computers, these states are represented by electricity in the processor. Electricity on means 1, and electricity off means 0. As their name suggests, quantum computers, on the other hand, use quantum bits, or qubits for short. These can also assume the state of 1 or 0, but they have another remarkable ability that clearly distinguishes them from classical bits. A qubit can also be in the state of 1 and 0 at the same time, or theoretically, in an infinite number of states in between. If we imagine a classic bit as a coin that either shows heads or tails, a qubit is like a coin thrown into the air that spins rapidly. As a result, we cannot say which side is currently facing up because it is in both states at the same time. Ultimately, it's precisely this property of the qubit that makes a quantum computer many times more efficient than a conventional computer. It needs significantly fewer qubits than bits for the same calculation. In a conventional computer, 2 bits can only represent one number at a time, but as already mentioned, a qubit can assume an infinite number of different states simultaneously. Even if we only assume 2 different states at the same time, each additional qubit exponentially doubles the number of simultaneously representable states. While 3 qubits can already assume 8 states simultaneously, with 300 qubits, it's as many as 2 to the power of 300, a number greater than the number of particles in the universe. But that's not all. In addition, qubits in a quantum computer can also be quantum entangled, which means that they are coupled to each other. In colloquial terms, as soon as a qubit is brought into a certain state, the state of its entangled partner also changes at that moment, mind you, at faster than light speed. This is why calculations in a quantum computer can be carried out faster than the speed of light. What does all this actually achieve? Or, to put it another way, what practical uses do these wondrous devices actually have? Well, none at the moment. But as soon as the technology advances, scientists want to use supercomputing power to simulate the interactions of molecules or their possible states, leading to breakthroughs in drug development. AI could also take a giant leap forward with the help of quantum computers. Additionally, the development of new materials and the fight against climate change could benefit from this futuristic technology. For the time being, we simply cannot foresee exactly how many applications quantum computing will have. Some experts even assume that we will use these computers to simulate all of nature's processes, finally cracking the great secrets of the universe and answering the question of the origin of life. Why qubits pose problems for researchers? All of this, mind you, is only possible with the help of exotic computing and information units. But how is a quantum bit created in the first place? Experts have various options at their disposal to generate qubits. Google uses special quantum chips on which weak currents flow in circles in the smallest of spaces. Each circulating current represents a qubit, and similar to ions, it can be brought into different states and read out with the help of microwave radiation. The aforementioned Willow quantum processor, for example, is equipped with 105 superconducting qubits. Aside from that, it is also possible to create qubits by trapping ions in magnetic and electric fields. Once trapped in this ion trap, they too can be brought into different states using microwave radiation and thus loaded with information, at least in theory. In practice, however, the field of quantum computing still faces significant challenges. After all, there is a reason why we're not all walking around with a quantum smartphone in our pocket. To manipulate and capture the moving particles of the qubits, they must be immobilized by cooling them almost to absolute zero, -273.15 degrees Celsius. Furthermore, qubits are extremely sensitive, and any disturbance, no matter how small, destroys their quantum state. Despite efforts to shield them from vibrations, magnetic fields, and other external influences, qubits remain stable for only fractions of a second. Calculations must therefore be completed within this very short period of time. To make this feasible, researchers must constantly increase the number of qubits working together, but this is easier said than done. Although quantum computers with 1,000 qubits made of ions or superconducting quantum dots already exist, researchers suspect that the quantum computers of the future will need millions of qubits to be truly practical. However, the more qubits a quantum computer has, the more unstable and error-prone it becomes, requiring complex error correction methods. For example, in the case of Willow, scientists implemented a so-called surface code, meaning that quantum information is no longer stored in a single qubit but distributed across several physical qubits. Together, these form a logical qubit, a computing unit. This way, the necessary information is preserved even if a single physical qubit makes a mistake. But perhaps, and this is the exciting part, this scaling problem can be avoided with the help of teleportation. How Oxford scientists teleported a quantum operation. To avoid misunderstandings, it should be noted that quantum teleportation differs from the science fiction version seen in Star Trek and similar stories. While teleportation in fiction refers to machines that can transport matter from one place to another at the push of a button, quantum teleportation describes the transfer of quantum information, such as the spin state of an atom, to a distant second atom. Oxford scientists are using modular quantum computers for this purpose, with each module containing a relatively small number of qubits. These are connected to each other via classical and quantum channels. While the individual quantum modules remain relatively stable, they can execute larger quantum algorithms when combined. Recently, experts at Oxford succeeded in coupling qubit modules in such a way that they solved a quantum algorithm across modules. Each module consists of 2 qubits, a calcium ion, which acts as a circuit and additional qubit, and a strontium ion, which serves as a network qubit. The latter is connected to the network qubit of the second module via an optical fiber. The collective calculations begin with the network qubits becoming quantum entangled. Photons, coupled to one of the qubits, act as matchmakers, establishing the entanglement. Each module then generates a controlled Z quantum gate, CZ, between its network and circuit qubit. The trick is that the entanglement of the modules causes the quantum gate to be teleported, meaning the qubit operations in both modules effectively run in the same gate. This enabled the Oxford researchers to connect separate quantum processors into a single fully connected quantum computer. Their modular computer successfully solved the so-called Grover algorithm, marking the first time a distributed quantum computer executed an algorithm through real interaction between separate modules. According to scientists, this breakthrough could pave the way for larger, more powerful quantum computers and even form the foundation of a future quantum internet.